Good afternoon. We're Group F, and today we'll be presenting our Case 2 study on National City Bank. My name is AJ Rivera.
My name is Michael Frick.
My name is Jim Lee.
My name is Vidur Nayyar.
So in looking at the Case 2 study, we were asked to create a customer propensity model for a new product, which was a line of credit against a household's used car. We were also asked to identify the next top 100 customers from a prospective customer list that the bank would then contact. In order to do this, we examined historical data from 4,000 previous calls and mailings for the line of credit offer, and then used this historical data along with some supplemental data to create the propensity model, evaluate it, and then identify by the unique ID top 100 households to contact from the prospective customer list.
To create this propensity model, we used the previous customers' marketing results and enriched the data with supplemental information from Axiom, credit history, and vehicle data. We split the data in two parts. One was the training set and the other one was test set. The training set comprised of 80% of the data. The test set was 20%.
According to SEMA, which we've followed and explored in class, to sample, examine, modify, model, and assess, our next step was to go through the examine phase of exploratory data analysis. So as Vidur had previously mentioned, we were given supplemental information that could be used with the overall previous historical marketing of results. So by we're using a left join with the HH unique ID, which is a unique identifier per individual client. We're able to combine these data sets together and create about 29 overall variables. The Y accepted, which is the outcome variable that we're concentrated on to whether or not you accepted or denied the line of credit for the used car, which is also a classification output versus a continuous output. So all our models were modeled off of the classification or categorical output of 0 or 1. In this case, we also found that only 24 of the 29 overall variables were usable as independent variables. So obviously our dependent variable Y accepted was not usable to predict itself. And we wanted to also remove the data ID and HH unique ID that we used to identify the information across all data sets. They're not useful for prediction purposes, though they are useful for identification purposes. They really have no bearing on the Y accepted to the end all be all, and so those were removed, as well as the call start and call end that was provided in the historical data file because we didn't have any calls to the prospective customers yet. Those variables are not usable within that context. And so we each took a model to describe and predict what customers would pick. And we used these models and we chose ownership of one model. I chose decision tree, Michael chose KNN, Vidur to random forest, and AJ to logistic regression. In my case, choosing decision tree, and to briefly introduce it, is a methodology that, as the title suggests, is a tree-based model. And what you'll essentially do within the data is continuously split and partition each part of the data set to create a pretty logical set of rules to categorize each of the independent variables to describe the dependent Y accepted variable. Because it's partitioned, it's prone to overfitting. So if you partition to very, very specific segments, you'll create a very specific decision tree that is actually overfit and not entirely accurate. So you should train off of a large set and make sure that you test and validate off of the test set to get the most accurate result. Additionally, on the left side, you'll see a pruned version of our inevitable tree. So as shown to the left, this is a more simplified version of our overall tree that has incorporated some more cleanup work as well with what I applied with vtreat. In this example, we used the R library caret, which generated a couple of different decision trees with different complexity parameters. The complexity parameter is used to limit the size of the tree, and we decided on a complexity parameter of 0.01, which was the most accurate according to our graph. Additionally, through EDA, we found that 5 variables were not particularly useful for analysis, at least for this model. It was communication, days passed, head of household gender, pets purchases, and affluence purchases. The results of whether or not a client accepted or didn't accept the line of credit in previous results was not very indicative based on the variables provided from these. So there's no difference between telephone and cellular between the accepted and denied. The end all result of the test model, of the training model applied on the test set, was 74.5%.
Moving into k-nearest neighbor, the model attempts to classify certain k-value based on nearby records. Some pros of this are it's an intuitive, simple to use model. However, it does take a long time to run. So with big data sets, that can be problematic for certain businesses. It uses Euclidean distance to measure the distance between nearest neighbors. And as you can see on the right side, this is an example of KNN in action, where the red dot with a K of 3 would be identified as a class B, seeing as 2 of the 3 nearest neighbors are purple. However, when you have a K of 6, the red would be classified as yellow class A, seeing as there are 4 yellow and only 2 purple dots. So this is just an example of KNN in action. And now as to the case 2 data, we fitted the KNN model with the Y accepted offer as being the dependent variable, and all other 24 variables, save the ones we excluded in EDA, were the independent variables. KNN allows for a large number of variables and classifies the dependent variables relative to their nearness to the other variables. And in looking at this, we can see that on the graph on the right, the accuracy increased as the Ks increased. But the accuracy was at 72.88% after running the model on the test set, which is not as high as some of the other models.
Moving on to random forest. The motivation for moving from one classification tree to a collection of trees used for random forest is twofold. The first reason is that classification tree is a greedy algorithm whose output is dependent on the choice of the branches used, due to which it may point to a local optimization. Global optimization is either not feasible or too expensive. Whereas for random forest, it is a lazy learner and builds the tree by taking different subsamples of the training data and forces each branch to be optimized on a subset of all the features. Once the tree is built, the out of the sample prediction happens by looking at the observation features and determining in which group the observation would fall for each tree. 2 ways of aggregating the prediction are hard voting and soft voting. Random forest can be used as a predictive model for continuous and categorical variables. From random forest, we saw that customer details like recent balance, age, and last contact were amongst the most predictive in determining who is going to be a high propensity customer to buy a new product. We enriched the data using an external data set, which is from Car Query API. Now, this data set adds information about the vehicle that the customer has. Using this data set, we got a little bump in our Gini, improving our random forest model. The test accuracy of the random forest was 74.1%, and the out of bound accuracy was close to 80%.
Logistic regression, it's a popular and powerful classification method, but it can also be used for predictions in the sense that we predict the probability of a categorical outcome. Logistic regression relies on a specific model relating to predictors, and we must specify the predictors to include their form. We did this in our explore phase of SEMA. logistic regression is applicable in situations where the outcome variable, here in our case, Y accepted offer, is a categorical platform, and it focuses on the binary classification. So here we use yes equals 1 and no equals 0. Logistic regression can be used to classify new records where the class is unknown. So our prospective customer file did not have information in the Y accepted offer. So we had to model the Y accepted offer into one of the classes based on the values of the predictor variables from our previous customer data. One of the cons for logistic regression is that it's susceptible to multi-collinarity, and we may need to analyze to remove that. And multi-collinarity, it's assessed by computing a score called the variance inflation factor, which measures how much the variance of a regression coefficient is calculated. So the smallest possible value of variance inflation factor is 1 without multi-collinarity. Sorry. So our goal for the case study is to predict which class Y accepted offer will belong to, or simply to classify it into a yes, no. I used a cutoff score of 0.75 for the best results. The cutoff score threshold is normally a standard 0.5. We're making a balance between the false positive rate and the false negative rate. And we're trying to minimize the number of mistakes we're making. So in doing so, I increased the cutoff threshold to 0.75. I also used a caret on a 10-fold cross-validation to get a better accuracy. And the 10-fold cross-validation is basically, it's a technique that involves randomly dividing the data set into groups or folds of approximately equal size for better accuracy. And in doing so, I resulted in an accuracy of 79.75% after running the model on the test set. So the model we chose was logistic regression. It had the highest accuracy out of all of our models. Logistic regression had 79.75%. Random forest had 73.4%. K&N had 72.88%. And decision tree had 74.5%. Now there's a difference between logistic regression and linear regression, as you can see in the two formulas on the right on the chart. The linear regression is widely used statistical tool, but it establishes a relationship model between two variables, whereas logistic regression measures the relationship between the categorical dependent variable and one or more independent variables by estimating the probabilities. So that's why I went with logistic regression as opposed to linear regression. And this model gives us a more precise indication.
And looking at the results from the top 100 prospective customers, we can see on the left-hand side, 20 of the top 100 customers that we identified. And on this chart, we can identify by the unique ID, and then we also see the risk and the success probability. Looking at success probability, we can see that it's descending with 0.9999989 at the top, and then it descends down. And we classified it in this way to show which unique IDs would have the highest success rate, as well as risk on the other side. It shows the risk of these unique IDs. Now, if you look towards the right-hand side, this is this case in action and how it can actually monetize and gain financial gain for the bank. So we had our leads, in the case was 4,000. We then qualified and converted to 100 prospective accounts. And then hopefully the next step in this would be to reach out to these prospect accounts and see if we can't turn them from prospects into real customers, thereby making financial gain for the bank. It's just a little bit of an overview of how this whole case can be used for a real life example for a bank. Thank you for your time. This was Group F.